Hello everyone, welcome back to another video on the Mathnasium. We're going to start our engineering and robotics final review here. In this video, I plan to run through all the information that you're probably going to need for your final. You can write whatever you want down. You can use notes on your final. You can use notes from this. You can use notes from previous lessons. That is fine. Just make sure you are trying your hardest and making sure you're using today as a review day to get the information that you need down. So let's jump right in and I'm going to run through the whole semester in maybe 20 minutes or so, and then hopefully less than that. And then we should be good to go. Let's take a look. All right, so starting us off here. Here we have the engineering design process. This is the kind of the beginning of the road for what we did in class. And in the engineering design process, the first thing that we did, or the first time you saw this, was kind of like after the cardboard boats. I tricked you into learning what this is. And this process kind of has a direction. So there is no direction drawn in here. But it is, it does flow this direction and, ends up coming back this way. And so it says, ask, identify the needs and constraints is our first step. So basically, there's a problem. That's a problem at hand or some sort of thing that needs to be done. And we started with the boat, and the first thing that we did is we started researching, how boats are built. What are the parts of a boat? We had to have a frame of reference from which we needed to work. And so we started to see things that we liked when we were researching the boats or researching Rube Goldberg machines. We started to see the things that we liked and the things that we didn't like. And we started thinking of things that we could do ourselves. So we started dreaming up possible solutions. But before, we did that, we had to be able to operate under these things called restraints. Now, a restraint is like a restriction or a limitation. Constraints, right, is a restriction or a limitation that you are operating under. For the Rube Goldberg machine, it should be fitting on your table. It should have so many stages to earn full credit. You are limited by time. All of these limitations and restrictions are things that you are battling as engineers constantly. And engineers in the professional realm are also, looking at codes and laws that need to be rules and regulations, all of those things, safety. Those are all constraints that engineers operate under, but time is a brutal one and money is a brutal one too. So constraints, limitations, restrictions, all the same thing. Okay, you develop possible solutions. You select a promising solution. Typically, the planning stage, you're dealing with other people. Hopefully with the Rube Goldberg machines, you're working with a partner, and you guys came up with some ideas and ended up selecting something good. You built the prototype. That's what you're working on right now. You're testing it, and you should be testing individual stages of that prototype. And I'm sure as you tested, you noticed new problems that you had to go and research to solve. So this is a never-ending wheel that drives progression for engineering as a whole, and the furthering and I guess the development of our society as a whole. And remember, engineering, I'm not going to write everything down. If you're listening, you should write down key things that you think are important in your notebook for the video. So just because it's not written down doesn't mean you shouldn't write it down. So listen to the advice I'm giving you and jot some of those things down as you're listening to the video as well. So here's a big hint. What is engineering? Remember, engineering is solving problems with math and science, and really to benefit humankind. That's the goal. That's the goal of the engineering design process. Make things that are better, more usable, function well, to benefit the human beings. So, and this is what you do. You circulate this wheel and find problems, plan, create, test, improve, and the cycle repeats. Okay. After that, we started learning about different drawing techniques. So really quickly, I want to go over the differences between these. You'll see some similarities, and hopefully, some of these are coming back to you. We had oblique, isometric, 1-point perspective, and 2-point perspective. Now, all of them are, none of them are perfect, so to speak, but some of them definitely look better than others. Okay, there's one here that's truly distorted, and that is this oblique, the oblique sketch. These, with oblique, all of these edges are going at the same direction. So they're all parallel with an oblique sketch, which is not the case with a 1-point perspective sketch down here, which looks similar, okay? The similarities between these two is they have horizontal and vertical lines, and they have kind of one direction generally that they head off towards. So even though this one is going, we can see the top and right side, and this one we can see the bottom and right side of the A. They start with, a front face. Both 1-point and oblique start with a front face. However, these lines aren't parallel. They're heading for a point, and all these lines here are parallel. They'll never cross. So keep that in mind, the differences between oblique and 1-point perspective. All these edges heading to that vanishing point. With an isometric drawing, you have this front edge right here. That's kind of how you start the drawing, and then you make a box. But again, with isometric, you have the top and bottom, these lines being parallel. And that is not the case for 2-point perspective. These lines are not parallel. They're headed to a vanishing point, and you can follow those lines and see that. So basically, oblique and 1-point perspective are the same, except for here, the vanishing or the receding angle that we see, they're all parallel. Here, they're all heading for a point. With isometric, it's all parallel, which is not perfect, but it does look, pseudo-realistic. And here, they're all headed to a vanishing point. So just make sure you can identify between these 4 things and know what one is when you see it. So one thing to keep in mind, why do some drawing styles look realistic and others look distorted? Well, it has the idea of when you take something that is in higher dimensions, we exist in 3-dimensional space. That's where we operate. And so our inventions that we create exist in 3-dimensional space. When we try to put those on 2-dimensional space, like a piece of paper or a computer screen, you tend to lose a little bit of information. And here's an example of, the surface of our Earth. And so when you're losing that information, there's not really necessarily a good solution. So we came up with, we have these different drawings here, but I can't see, the back of the A. I don't know if there's anything behind it. Oh, I don't know if it's made of cheese and someone snuck up and took a bite out of one part of the A. I'm not sure. No one tells me these things. Man, it's late. I need to think before I talk. Well, too late. We're halfway done with the video. I'm not really stopping now. Okay, so when you go from 3 dimensions down to two dimensions, that's called a graphical projection. That's what we're seeing here. So all these are projections, and that's what we're doing when we're drawing our ideas. And so I taught you another drawing style called a multi-view sketch or multi-view drawing, where you see objects from multiple angles. And the purpose of this is because each of these by themselves do not tell the full story of the item that you're trying to create. However, if you have all of them together and label what you're looking at, and so from that multi-view sketch, this is the top, this is the front, this side is the right, and so you can kind of align yourself with these views. That means back here is the back, on this side is the left side, and down below is the bottom 6 sides for the view. So multi-view sketches are also part of your final. Make sure that you know or familiarize yourself with those. Okay, there are going to be questions about Onshape on the final. It's just a little quiz, so nothing to be too freaked out about here. I'm basically just going to ask you questions about the tools that you're using. Do you understand the big and important tools that you need to know? And what are those important tools that I want you to know? Well, it's basically these. Do you understand what extrude is? And here I have a student chess piece. This is Will's, I believe. What is extrude? Well, you take a profile, you take a sketch, and you give it a thickness. So you can see Will probably used extrude for the base of this really good looking chess piece that he made. So that's one thing to look at. Revolve, what is revolve? Well, that's when you take a profile and you spin that thing around an axis to create a solid. So all these things are creating solids. I'm not sure if he had revolve here, maybe to make the crown in the chair. Okay, or the ends of the swords, the hilts of the swords here. And then we have our sweep. Do you understand like what sweep is? You're taking, a profile and sweeping it along a path. And then loft is connecting two sketches together to create a solid. So all these things are our solid creation tools, and I do want you to know those. There are some other important tools to know. Mirror, for example, the pattern tool, linear pattern tool, trim, fillet, and then this is the big one here, dimension. Dimension allows us to move things around. In a sketch, it also allows us to change the size and the distance of things in a sketch. So make sure you know those, as well as the plane tool. So I might just have a question like, oh, which best describes what here's what this tool does, which tool is it, and you have to choose. Okay, so please make sure you understand those tools. If you need to get back in Onshape and familiarize yourself, or go watch some old videos, you can. Fillet, trim, mirror, circular pattern, dimension, plane. Okay, we're moving on to this last unit here, mechanical advantage. Remember, mechanical advantage is something that it's an advantage that we use or we manipulate as engineers to make devices more usable for human beings. I mean, that's the gist of it. And we don't always use it to make ourselves more powerful. So for example, sometimes we use our knowledge of simple machines to generate a force or multiply our force, make us stronger than we actually are. But that comes with a cost. If you have a mechanical advantage that is bigger than one, you are generating a force with that system. This is really important stuff. And it comes with a cost, and that cost is generally you're going to have to move a greater distance in order to get that trade-off. Okay, and we're going to see that in a couple examples here. If you have a mechanical advantage that is equal to one, that means that the machine does not change the input force that you will have to use. Essentially, the machine's not helping you in any real way. You're putting the same amount of force in with the machine as you would without it. So an example of that would be, let's say with pulleys, if you have just a fixed pulley, you're trying to lift somebody, a fixed pulley redirects force, but it doesn't lessen the force that you will need to lift somebody. But you can use your weight, I suppose, in that instance. But still, we would say that's a mechanical advantage of 1 and not 0. If it's not helping, the mechanical advantage is 1. All right, if you have a mechanical advantage less than 1, a decimal like 0.5 or 0.068 or something like that, that means that the machine is being used to generate a speed. Now, generally, if something generates a speed, it comes with a cost. And that cost is you have to put in an additional force. Okay, and we're going to see some examples of that. What is mechanical advantage as a whole? It's really calculated in what is the force. It compares the force when you're using the machine to the force when you're not using the machine. So if you divide the force when you're not using the machine by the force when you are using the machine, that will give you the mechanical advantage. Okay, let's run through our simple machines really quickly. We have our inclined plane with just slope length divided by height. Basically, instead of lifting these boxes directly up onto the truck bed of the U-Haul, this person is using the ramp. They're putting in much less force as they pull those up the ramp versus having to lift them directly into the truck bed. Okay, and so if on your quiz or on your final, what I might ask you is something along the lines of, hey, I'll have some water. Great, I'm going to get a quick drink here. Oh, man. Good stuff. Oh, all right, so if you want to figure out how much less force this person is putting in, all you have to do is calculate the slope length and the height if they're going up. So let's say they're hauling those boxes. Let's say the boxes weigh 100 pounds, okay? And they're hauling the boxes up, and the height in the picture here, let's say that is 2 feet. Okay, I know that's a little bit hard to see. So the height's 2 feet, they have 100 pounds, and the slope length here, I'd say that looks like about 10 feet. So if you're doing that calculation, and let me make sure I have this one in as well, this distance here, 10 feet, that would give us a mechanical advantage of 5. We would do 10 divided by 2, the output height. This distance is not something we need to consider unless we have to use the Pythagorean theorem to find one of these other two sides. So it's really the slope length that the person is on and the height. Input divided by output. Okay, so with this person lifting these boxes and they have this mechanical advantage as they're walking up the ramp, if you divide by 5, they're putting in a pulling force of about 20 pounds to get that 100-pound load up the ramp. Pretty exciting. Okay, moving on. Yeah, cool. Yeah, let's move on. Okay, the wedge. Here's a set of needles. If you want to calculate the mechanical advantage of a wedge, then you can look at the thickness of the needle and the length of the needle. Where it's straight, that part doesn't matter, only where the wedge portion exists. So it's length divided by thickness, the long divided by the thick, to figure out what how this particular wedge is helping you, okay? And maybe it's a little more complicated than that because, maybe it's thinner one direction than the other. So you have to take a look, and, this one is a little more complicated. They're all different needles. I just chose one to measure. Okay, this is a needle, and a needle does count as a wedge for separating things like skin with a shot or fabric and material on a sewing machine when you're working on those. Okay, so that's a wedge. Okay, the screw, just need to know certain things like this right here is our diameter. Make sure you have this equation somewhere. Okay, we have our diameter, and the pitch is the distance between the threads. So if you want to calculate the mechanical advantage here, you just plug it into this formula. Let's say this bolt is, I don't know, 3.5 inches. If this bolt is 3.5 inches wide, and the pitch, the distance between the threads, that's this tiny little distance here, is like 0.07 inches, 0.07 inches, then we can go to our calculator and we can quickly do this calculation. So that would be 3.5 times pi, 3.5 divided by 0.07 would give us a mechanical advantage of 157. So I did 3.5 times pi, which is 3.14, divided by the pitch, and we can calculate the mechanical advantage of a screw. That's great. Moving on. All right, levers. This is a big one. All right, so levers fall into 3 classes, Every lever system should have a load, an effort, and a fulcrum. The load is the thing that is being acted upon. In the hammer, it's the nail being pulled out of something. The pliers, it's the thing that's being gripped. The wheelbarrow, it's the dirt. That's the load that we are acting upon, we're lifting. The nut in the nutcracker, the sugar cube in the tongs, and the thing that's being lifted in our arm is actually a third order, third class lever. So order and class are really the same thing, okay? So this is where it goes to the mechanical advantage falling into three categories: greater than 1, less than 1, equal to 1. All right, so most of the time, first and second order levers are used for mechanical to generate a force. And in every instance here, you're generating a force. You're pulling out a nail that you need to amplify your force, but you're going to have to, move that over a greater distance with the handle of the hammer. No big deal for us. With the pliers, kind of same thing, being used for force depending on where you grab. Wheelbarrow definitely being used for force to lift the dirt, and so on and so forth. But these ones are not. Our arm, in general, based on where the fulcrum is in our elbow, and then the head of our muscles attached to our arm onto the lower arm to be able to pull and lift in different directions. Okay, so our arms and our limbs count as third class levers. They do generate a speed in a sense. I also used brooms and rakes in this category and fishing poles. So all those things. Remember, mechanical advantage is effort arm divided by load arm. Effort arm divided by load arm. The effort arm is the distance between the effort and the fulcrum. So please be careful. You're not always just measuring to the center line. This is the effort arm. The load arm would be this distance here. So that's load arm. This is effort arm. Please be careful. Third order levers are always used for speed. Second class are always used for force. And force can be either, but generally they're used to generate a force. Okay, I think I covered what I need to for levers there. I think. We'll take a look. I think so. Talked about class, talked about the calculation. Yeah, I think we're good. Pulleys. For a simple pulley system, remember there are other pulley systems, but for a simple pulley system, the mechanical advantage is not necessarily equal to the number of pulleys. It's equal to the number of rope segments supporting movable pulleys that are really supporting the load. Okay, so since here you have 1, 2, 3 segments supporting the load, that 72-pound load, we have a mechanical advantage of 3. Okay, we have a mechanical advantage of 3 in this instance. So what does that mean, and how can we make sense of that? Well, if you have a mechanical advantage of 3, it means that the amount of weight that I'm lifting with this rope is the same that is on this rope here, this last check mark. So each of these is sharing the 72-pound load. Each of them should have 24 pounds. 24 times 3 is 72. So I should have 24 pounds of force attached to the rope that I'm pulling here. But that mechanical advantage, remember, comes with a cost. And the cost is this. If I want to raise this load, say 2 feet, I'm going to have to pull out, if I want to lift the load 2 feet, I'm going to have to pull out 6 feet of rope, right? We don't get something for nothing. Because we have we're making ourselves stronger, essentially, comes with a cost. And that is 3 times the distance. We multiply our force by 3. That means we have to pull out 3 times the amount of rope to lift the load. So these questions can fall into a couple of categories. I may not tell you the mechanical advantage in the question. I might say, Billy is lifting with 24 pounds, a 72-pound load with 24 pounds. What's the mechanical advantage? I might say something like that. Or I might say, Billy pulled out 100 feet of rope to lift the load 5 feet, whatever. What's the mechanical advantage? And then you would have to do the math to figure that out. So please make sure you're kind of in line with those. Please look at some of the other examples that we've done as well to answer those questions there. So I think we've gone over most of this. So this is a simple pulley system. There are other pulley systems where you can get incredibly high mechanical advantages, like we saw with the tractor ripping the tree out of the ground. I kind of talked about there's complex and compound systems where you can get, with just a couple pulleys, you can get very high mechanical advantages, but those systems often need to be reset. So please be mindful of that. This is what I asked for Christmas. This is my, man, what a beaut. Look at that bike. I'm telling you, that is, yeah, it's just what I've always wanted. And I can't wait to ride it and see my neighbors and just gaze upon me in jealousy. That's what I'm looking forward to here. All right, so a bike has two kind of wheel and axle systems, main ones that operate. And I didn't really think about this when I taught the lesson. I should have. The first is the one, the pedals. And generally you look at, it's a complicated system, but the system down here has a mechanical advantage that is, and I didn't do chain drive, but that is also a calculation here. I wouldn't worry about it too much, but mechanical advantage here is less than 1 because the bike is used to generate a speed. You have to put in an increased force on the pedals, but it generates a speed for you on that, on the back wheel that will then propel you forward faster than you'd be able to, if you, like when you move your feet in a circle, 10 feet, you don't move 10 feet on the bike, you move much further, okay? But there's another wheel and axle system here. So the gears and the wheels have a mechanical advantage that is less than 1. This generates a speed. But you also have the wheel and axle system of, say, the handlebars. The handlebars have an axle, that turns the front wheel to steer. It would be much harder to turn a bike if the handlebars were only this wide. You would have quite a bit of force that you would have to put in to those handlebars. And so the fact that the handlebars are separated on this beauty of a machine, that allows us to not have to put as much force to be able to turn the bike. So here we're multiplying our force, but the cost is we have to move our hands further. So here we have a mechanical advantage that is greater than 1. This is being used, the handlebar system to turn the front wheel is being used for force, and the pedaling apparatus on the bike, the gears, the pedals, the sprockets are being used, to generate a speed. Please make sure you are careful to note the questions on the final when I talk about radius and diameter. I'm going to encourage all students to show their work on a piece of scratch paper. You need to submit that work to Mr. Armstrong when you're done. But number the questions, or you don't have to number the questions, just separate them out on the sheet of paper. But you might need to draw a picture. I want you to really take your time before you answer these, because some are a little tricky, and you might need to read twice. I would encourage reading every question 2 to 3 times prior to submitting and double checking your answer. You're going to have plenty of time. It's not very long. Okay. Mechanical advantage for a wheel and axle system is input diameter divided by output diameter. So like with the handlebars, you could use radius as well if you'd like. If you were to find the mechanical advantage of these handlebars, you would, imagine drawing a line out here and go to where your hands are gripping. So you'd measure this distance here. That would be your input radius. And then your input radius is going to be longer than your output radius, which is going to be this tiny distance on the axle. So we have a very large mechanical advantage, like 10 or something, on this awesome, beautiful bike that I really hope Santa brings for me. And then lastly, what I want to talk about here is, do simple machines change the force we apply to a system? The answer is yes, they do. They change the force. They change the force at any given instant. What do they don't change is the work done, okay? If I go up a handicap ramp to get into a store, in theory, I've used the same amount of energy to get up that ramp as if I had just walked up a steeper ramp to get to the same spot. It just takes longer. I have to use it over a greater distance. So here the answer is no. Do simple machines change the work done in a system? Nope. They only change the force at any given instance. So please remember force. Force was this Isaac Newton's 3 laws of motion. Force was the second law. Force equals mass times acceleration. If you need to know that. Mass measured in kilograms, acceleration measured in kilograms second squared or something like that. Meters per second squared is acceleration. So this is kilogram meters per second squared. The units of force are newtons. So make sure you remember that. And the units of work are measured in energy. Work is equal to force times distance, and it's measured in a unit called joules. So please make sure you got that down as well. All right, that's basically it for the video. I'm not doing any crazy in-depth calculations here. I believe you guys can do it. You can use your notes, go back, review those notes on some of those simple machines if you need to. There are videos posted for those as well if you want a more in-depth description. Thank you for watching, yeah, hope you guys are doing well. I miss y'all, and have a great day.